Hello class, welcome to the Stat 511 Lecture 2 video. In this video, we are going to focus on constructing a stem and leaf plot, distinguishing between statistics and parameters, understanding the importance of randomization and sampling, distinguishing between types of samples, understanding the impact of bias on study results, identifying sources of bias, learning the terminology for experimental design, understanding the 4 principles of experimental design, understanding the difference between an experiment and an observational study, which we discussed a little bit in our previous lecture, and distinguishing between a retrospective and a prospective study. Now, in our previous lectures, we started off with the definition of statistics, and we talked about the collecting and the design of experiment purely in the definition. We're going to get to that aspect of statistics a bit more in this lecture. To begin, there was one more graphical display I wanted to discuss, and that is the stem and leaf plot. And this is a plot where each value is split into a leaf and a stem. Now, usually the stem is the trying to see the proper way to call it. I want to say the most superior digit, but in the sense of if we were having, say, the number 44, the stem is, in this case, the 40s. The leaves are each of the ones place values. Usually with a stem and leaf plot, it is important to provide a key just so the reader knows what the stem's place is and what the leaves place is. In this case, the stems are the tens place and the leaves are the ones place. So we have a value of a stem of 4 and a leaf of 4. That is 44. We also have 46, 47, and 49. Notice, even though there's no value in the 50s, we still have to record that number. Same with the 90s. We aren't allowed to skip stems. Where we stop and where we end, we have to state each subsequent stem. Let's do a quick example. I find it easiest to record my numbers from least to greatest. So this will become 2, 6, 9, 24, 27, 34, 39, 45, and 45. So to begin construction, I make my T, stem, leaves. I usually begin by writing out the stems first, and we are going to let each stem be the tens place and each leaves be in the one place. So we are going to have to go 0, 1, 2, 3, 4. So my leaves for the 0 stem will be 2, 6, 9. We will have no 1 for our leaves. 2 will be 4 and 7. For the 30s, we have 4 and 9. And then for the 40s, we have 5 and 5. And that's it. That's a stem and leaf plot. Now, this plot does have uses when we are trying to understand the distribution, as far as if we wanted to see if our distribution was symmetric or skewed, kind of like a histogram. Because if you were to rotate your screen, you could see the leaves in many ways act as a histogram, where our stems are histogram bound. So instead of having to write out 0 to 9, the stem of 0 represents the bandwidth from 0 to 9. Also, this is really good if we're trying to find if we have any modes. Okay, so that was the last of the graphical displays that I was interested in talking about, and the ones that I feel that are most important for you guys to be aware of. Now, as with most first chapters in any course, we do have quite a bit of definitions still to talk about. Now, this slide talks about the difference between a population and a sample. These next several definitions are pretty important because they are something that we will continuously refer to starting really this whole course, but it does play a major factor in the first part of chapter 2 and heavily in chapters 3, 4, and 5. So what is a population? Well, it is the complete set of people or things being studied. For an example, we might say every member of the entire population of the United States. A census is the collection of data from every member of that population. So here in the United States, every 10 years, they take a census of the population of the United States and to collect all of that biographical information. Where do you live? How old are you? What do you live? Where you live, how old you are, race, gender, things of that nature. That's not the only thing a census studies, but that is a good example, is the census that is taken. Next, a sample. A sample is a subset of the population from which data are actually obtained. In most cases, taking a census is impractical and impossible. The United States only does it once every 10 years for its population, but it is time consuming and it is expensive. What happens instead? Usually people take samples. If you think about all of the elections that occur, if you read the news or watch the news, you'll often hear the news reporters talk about polls. Those polls are samples, and they use samples to make inferences about the population. So the sample information is used to predict or inform about the entire population. And that is something that we really focus on in chapters 3, 4, and 5, are how to use information from a sample and use that to inform our decisions about the entire population. When we do the reverse, we take information about the whole population and try to predict what our results would be from a sample or inform on a sample. That is probability, which is what we'll focus on in chapter 2. Now, raw data. This is the actual measurements or observations collected from the sample. Now, if you recall, the very first informational slide in the first lecture, I gave you a definitions singular, which was the science of collecting, organizing, and interpreting data. Statistics also has another word, which is the numbers describing characteristics of a sample found by summarizing the raw data. So, when we take a sample from a population and calculate the mean, that is the sample mean, and it is an example of a statistic. If we had a census and took an average, that would be a population mean. And that would be a good example of a parameter. So a statistic is a numerical measurement describing some characteristic of a sample. And we often will be able to easily calculate these, such as the sample mean, the median, and the standard deviation. A parameter is a numerical measurement describing some characteristic of a population. Usually we are not able to calculate this without a census, and we instead will estimate our parameters with statistics. So there are two main types of statistical analysis: descriptive statistics and inferential statistics. Descriptive statistics are numerical and graphical summaries of data, and its purpose is to summarize. In inferential statistics, we draw inferences from sample data for the whole population, and we use this to predict or to explain. What we did in the previous lecture was focus on descriptive statistics. The majority of this course is going to focus on inferential statistics. Now, sampling is a pretty big concept for statistics because our statistics that we use to explain, predict, or summarize a population needs to be representative of the whole population. So from our slide, since it's usually not feasible to take a true census, we want to compute statistics that are a good estimate of the parameters. A sample that achieves this good estimation is a representative sample. When the estimate of the parameters are way too high or way too low, it is usually the result of some sort of biased sampling method. So what is bias? Bias is a problem in the design or conduct of a statistical study that tends to favor certain results. Studies conducted with methods that tend to overestimate or underestimate the true value are said to be biased. A study conducted by a procedure that produces the correct result on average is said to be unbiased. You often hear in the news when you're hearing about politics, you hear the word biased thrown around. And this is sometimes a result of the information that you are hearing from. So talking about an example of bias sampling when it comes to voting and polls. We know that certain parts of the United States tends to favor certain political groups. For example, California tends to be very supportive of Democratic candidates, where Texas tends to be very supportive of Republican candidates. So, if you were to take a poll of Texas, chances are it's going to favor, say in a presidential race, it's going to favor whoever the Republican candidate is. If you were to poll in California, it is going to be biased towards the Democratic candidate. And so neither of them are going to be very accurate ways to predict who is going to be, say, the next president of the United States. So from my perspective, a lot of times when we have polls that will say, oh, so-and-so's in the lead, they're, going to win, and then lo and behold, they don't win the election. From my perspective, that means that there was a faulty sampling or some sort of bias, meaning that the people collecting the information did not do a good job of doing an unbiased sampling. So your results were incorrect as a result. So let's take a look at another example of bias. In an effort to estimate the percent of U.S. college seniors who have attended at least one college football game, we take a survey of the seniors in this class. How is this study biased? Well, for one thing, this is a graduate level course. None of you are seniors. So that means that according to this poll or this survey, no one attends a college football game that is a senior. If I were to take this in, say, an underlevel statistics course, I may have a few seniors, but not every senior from every major is going to have to take that statistics course. So it's not going to be truly representative of the entire population, which in this case would be the senior class. One very important thing in order to have an unbiased sampling is randomization, meaning that each individual is given a fair random chance at selection. And this protects against bias from factors you know in the data and then factors you don't know that are in the data. What do I mean by that? Well, go back to our polling example. Is if we take a list of all registered voters and randomly pick, say, 1,000 voters from the United States, yes, you're going to have some that are going to come from Texas. You're also going to have some voters that came from California. That is some of the bias that you know. But also, you don't know about maybe one of the people on your list happens to be someone of a very extreme political beliefs and is going, or on the opposite end, someone who's planning on writing in Mickey Mouse. By randomly selecting, you should be able to capture all the different parameters of the population. Now, ideally, we call simple random sampling, we abbreviate it as SRS. So suppose we want to take a sample from a population of 200 students. We order the students from 1 to 200, and then we use a computer to randomly select 50 students from that 1 to 200. A simple random sample of size n is when every sample of size n has an equally likely chance of being selected. SRS is the standard by which all other sampling techniques are measured. Our statistical theory is going to be based on the idea of simple random sampling. We know in reality this is not always fully practical. Going back to our polling example, well, not every single registered voter is going to actually vote. So if you're not planning on voting, then your opinion is not going to be as important. Another thing we care about is sampling frame. The sampling frame is the list of all subjects from which the sample is drawn. Deciding on the sampling frame can be difficult. If you want, say, students at WVU, do you include part-time students, online students, students who are studying abroad, students who are on leave for a semester? How do you decide what classified as a student at WVU within the parameters of your experiment? Another concern we have is sampling variability. That is, we have to understand that samples will vary from one to the next. Take, for example, we sample the weights of 5 students. Our first sample might have an average weight of 131 pounds. Then the second sample of 5 students might average 138 pounds. This sample-to-sample difference is called sampling variability or sampling error. And this is a natural occurrence. That doesn't mean that there's any bias, but what it does is it allows us to determine the accuracy of a statistic for a parameter it is intended to estimate. So basically what we're saying is A single statistic in general is not going to be perfectly representative of a parameter. It will, however, be close. So by maybe taking a few samples and then averaging them together, we might have a better picture of a true parameter. Or something we'll focus on is something called a confidence interval, where we will do a sample, get, say, the sample average of, say, the 131 pounds of being the average weight of students at WVU. And what we'll do is we'll calculate a margin of error, saying, okay, well, we believe that the average weight of students at WVU are 131 pounds plus or minus 50 pounds. Another type of sampling is called stratified random sampling. In stratified random sampling, the population is divided into groups called strata. Then a simple random sample is drawn from each stratum. This is useful when the strata differ from one another, but the individuals within a stratum are similar. So we could theoretically divide our strata by, say, classes. So we have freshmen, sophomore, junior, seniors, and graduate students, and then pull, say, 100 random students from each class. One example of a stratified random sample is that a company has 800 full-time and 200 part-time workers. To draw a sample of 100 employees, a simple random sample of 80 full-time employees is selected, and a simple random sample of 20 part-time employees is selected. Now, this kind of sampling is actually very smart because it will keep that ratio of full-time to part-time employees intact while still getting a comprehensive information from the group as a large. Another type of sampling method is called cluster sampling. In cluster sampling, the population is divided into groups known as clusters, and these clusters are randomly sampled, and all the members of the selected clusters form the sample. Cluster sampling is useful when the population is too large and spread out for simple random sampling to be feasible. So to kind of show you this visually, imagine this large circle is an entire population. And we take little group clusters and we sample everyone in these little subpopulations, all these little groups, and get all the information about these small groups, and then use these random small groups to inform on the whole population. An example of cluster sampling: to measure the impact of a new teaching technique, a researcher randomly selects second-grade classrooms within a county school district. All kids in the selected classrooms are taught using the new technique, and then their outcomes are measured. This is a really good use of cluster sampling because it allows an entire class to be taught using a new method versus the old method without the individual class being affected. What I mean by that is it wouldn't be quite possible to take a class of, say, 30 students and say half the students learn one technique and the other half learn a different technique. That's not quite as easy. But if you have different classrooms within the whole county learning, some using the old system, some using the new system, then you'll have a better idea of the overall effectiveness of the new system. Another type of sampling is called systemic sampling. And this systematic sampling, items are ordered and every kth item is chosen to be included in the sample. And in this, you should start at a random spot, meaning you would sample every fifth item as it comes off an assembly line and checking its quality, or if it was a bag of chips, you might be checking its weight. Now, unfortunately, so all these sampling techniques, some are better than others, some we just have to make the best of what is feasible, but there are some known sampling mistakes we want to avoid. One is using a voluntary response sample. Why is this a problem? Well, this means that you open up the survey to many, but only a very few people would respond. Some examples of this would be internet polls, how are we doing cards, and radio call-in shows. A particular type of person is going to be willing to respond as opposed to the entire population, so this introduces bias. Again, this means that the sampling frame does not correspond to the entire population. It's prone to bias. And as I said before, only a certain type of person is going to respond, usually the most opinionated. Another type of sampling mistake is something called convenience sampling. And this means that you sample the most convenient people, such as asking all of your Facebook friends or Instagram friends, taking a survey at a shopping mall to find out how much people like shopping, asking people in a restaurant how often they like to eat out. A convenience sampling is always going to be biased. More likely, it's either to get people to like you, and it's not going to be representative of the entire population. Another type of sampling mistake is something called undercoverage. This is when a subpopulation is left out or underrepresented in the sample. An example of people who are often missed in undercoverage are people in prison, homeless individuals, students, long-term travelers, and cell phone users. Because generally a lot of times when we're doing polls, CNN, Fox News, they tend to call people's landlines. And only a certain type of the population still has landlines. And I don't know about you, but if someone calls and I don't recognize the number, I don't answer it. If it's important, they'll leave a message. And as such, I am not someone who is likely going to respond to the "who are you going to vote for" phone calls. Another type of issue or error is non-response bias. And this may occur when people randomly selected to participate do not respond. Non-respondents may differ systemically from those who do respond. This is difficult to measure since you cannot reach out to people who are non-respondents. And this is something that we just generally have to kind of compensate and deal with. In my work, there is a very long-term project dealing with police officers. And this longitudinal study has been following these police officers for 20 years. And what is going to happen, of course, is over the span of it's really more than 20 years, is as the years go on, more and more participants are going to drop out. They're not going to want to keep doing it. In my study in particular, it's not necessarily the most convenient thing because we're having people fill out tons and tons of surveys, and we're taking blood pressure and physical measurements, blood work, and and we do it every 5 years. And for some people, that's a lot of work and they don't want to do more of it. But it does affect our study, and it is something that I have to adjust for. Another type of issue which is the opposite, it's the response bias. But it is not the opposite. I know I just said it, but it's not. Opposite in name, not opposite in actuality. Response bias is anything in the survey design that influences the responses. There are some social acceptability bias, meaning people want to please the interviewer, they don't want to admit flaws or illegal or shady behavior. People like to hide personal facts like income, age, etc. And also sometimes the survey, whether it's paper or person, the questions themselves might be leading bias, meaning how do you feel about the terrible acts of such and such a thing? Well, by you putting the word, how do you feel about the terrible acts, you're telling the person you're asking how to feel. That's not truly getting the kind of unbiased information that we want as statisticians. So here's the nice example of what would be an ideally randomized experiment. So scientists want to determine which of 3 types of seed, A, B, and C, will result in the largest wheat yield. So what we do is we will prepare 12 identically sized plots of land with similar soil types. Plant each type of seed on 4 different plots, choosing the plots at random. We will water and fertilize the plots in the same way. Harvest the wheat and measure the amount grown on each plot. And then we will be able to compare the wheat yield by seed type. That is a nice idealized sample, and it is kind of one of those the best we can possibly do to eliminate sources of bias. Now, as we've talked about an experiment, we now need to learn the proper terminology of an experiment. So one is experimental units, and this is the subjects on which an experiment is performed. For example, people, parts, companies, or plots of land. We have the outcome or response, and it is what is being measured on each of our experimental units. So in this case, the wheat yield. A factor is a variable whose levels are manipulated by our experimenter. So for example, the type of seed planted. And then the level is a specific value or a factor of a factor. So for example, seed type A. Still using our wheat yields. So suppose we have 2 factors, seed type A, B, and C, and then also fertilizer type 1 and 2. So in this case, suppose we are interested to see not only what seed type is best, but also which fertilizer type is best. A, B, and C are our levels of seed type factor, and 1 and 2 are the levels of the fertilizer factors. This implies that we have 6 possible treatments: A1, A2, B1, B2, and C1, C2. One possible option would be that we could randomly assign our 6 treatments to the 12 plots. Treatments are the combination of levels of 2 or more factors. So for example, A1, that implied seed type A with fertilizer 1, or the different levels of 1 factor. When we only had the 1 factor in experiment, we simply had seed type A, B, and C. So what really is an experiment? Well, an experiment manipulates factor levels to create treatments, randomly assigns subjects to treatments, and then compares the responses of the subject groups across the treatments. So this is a nice diagram of a randomized experiment. We start by a random allocation of our resources. So for example, we might split our things into our 2 groups, then apply our different treatments, and then compare the results of our treatment. Once again, I can't emphasize enough how important randomization is. Now, why is it so important? Well, we want to be able to detect the differences between the treatments. This is impossible to construct treatment groups that are exactly alike. In a randomized experiment, any differences between the groups are likely to be small, and we can conclude that any differences are going to be due to the treatment. But this is not true if participants choose their own groups, or if we decide on what is, quote, best for them. So one example of that would be, say, a medical study where you're trying to determine a new type of, say, cancer treatment, and you decide to give the new treatment to the people you like. You know, you're like, oh, these people have a nice sob story. I'm going to give them the treatment. And the people that were cranky and I didn't like, I'm going to give them the placebo. No, that doesn't work. That's biased. And it could be that, you know, attitude might also have an effect on how well your treatment goes or how well you follow up with the treatment protocol. So it means your results are going to be biased, potentially invalid, because you didn't properly randomize. So an example could be pet food safety. So beginning in March 2007, there was a wide recall on many brands of cat and dog foods due to contamination with melamine and cyanuric acid. Thousands of pets died of kidney failure. We know that one specific brand, brand A, is safe, but we are unsure about brand B. And we want to know, how would we design an experiment to test if brand B is causing kidney failures in pets? Well, one issue for us would be that we can't just assign, say, dogs to brand A and cats to brand B, because then we wouldn't know whether, if an animal died, so dogs got A, cats got B, we wouldn't be able to fully determine if dogs were also ill from brand B if all the deaths occurred in just cats. So we would need to randomly assign various animals. Now, this brings us to talk about the 4 principles of experimental design. And these 4 principles will allow us to make the best experimental design as possible. So one thing that we care about is control, and that is that we make all conditions as similar as possible for all treatment groups. Our control will allow us to isolate the one thing that is being studied. So for example, in our pet food experiment, we would start with, say, one type of pet, say dogs, and we would control the food and water portions, housing, exercise, and sleep. And we'd also only use one specific breed of those dogs and control as much as everything else. Next, we are going to randomize, and that means we equalize the effects of variation that we cannot control. This distributes the uncontrollable factors equally. So still using our pet food example. So after we've controlled for all other factors, we would randomly assign the dogs into the 2 groups. The saying is, control what you can, randomize the rest. Next, we're going to replicate. So now we've done our first round of experiments. We've applied each treatment to our number of subjects. We repeat, as I said, the entire experiment on an entirely different population of experimental units. So using our pet food example, we will now assign more than 1 dog to each food treatment, and we'll redo the entire experiment, this time with a different breed. Next, we have blocking. So as I said at the very beginning, that there is an issue if you only test for dogs and not for cats. So we have to consider the safety of all the animals. So how can we design the experiment so that the differences between cats and dogs don't mess up our attempt to see differences in pet food safety? Well, in that case, we let each pet type be a block, a group of subjects that are similar in a particular way. So what it is when we block, we separate our data into our groups, in this case our cats and dogs, and then we will randomize our treatments within each block. This design is called randomized block design, and it helps isolate the variability due to differences between our blocks. And it also helps us clarify the differences between our treatments. Types of blocking, as we've already heard before, stratification. Now, another issue though, particularly when we do blocking, is called confounding. So two factors are confounded if the levels of one are associated with the levels of the other. So example, which I kind of alluded to this earlier, if we assign brand A to cats and brand B to dogs, we won't know any difference in kidney failure rates is due to the brand of food or is it to the animal itself. Species has now become a confounding variable. Another issue we might have is problems with implementing a designed experiment. So let us consider studying lung cancer. Now, here's a problem. We cannot randomly assign people to smoke for 40 years and then measure the results. This is where observational studies come into play. We can't always go forward. Sometimes we have to look back. An example of this would be music and good grades. We could compare GPAs of music students and non-music students at Morgantown High, compare GPAs. Conclusions, looking at this, we would say playing an instrument, therefore makes a student smarter. Well, problem with observational studies is you may be just looking at two factors, but because you aren't able to properly control, this brings in issues like students who play instruments might have to balance their time more, and when you're forced to budget your time better, you tend to be more productive. But still, when we can't experiment, observations are the way to go. So how do they work? Well, in this case, researchers don't randomly put people into groups. Instead, they passively observe participants. This is good for discovering relationships related to rare outcomes, but it is truly awful, as you saw in the previous slide, for trying to establish cause and effect relationships. Now, there's two types of observational studies that we really focus on, and that is the retrospective studies and the prospective studies. A retrospective study is when we collect data on something that has already occurred. This is very important for when we study for or studying rare events. So take, for example, pediatric brain cancer. You can't randomize this, and you can't follow kids around until enough of them develop cancer. So instead, what we have to do is we look at children who've already developed pediatric brain cancer, and then we look back into their histories and try to find commonalities. The other possibility is the prospective studies. In this case, we would identify subjects in advance and then try to collect data as events unfold. So there is some pros to this. It means that it is possible to isolate variables, and then we can design our study to our specifications. So it more mirrors an experimental design. There is unfortunately some cons to this. It is expensive. Rare occurrences are going to require large samples. They can take a long time, such as, do breastfed babies live longer than bottle-fed babies? Well, I don't know any researcher who could, at least a single researcher who could follow that study to completion. So this brings us to the end of our second lecture. For you at this point, you should finish reading chapter 1, and you have all the information you need to finish the first homework assignment, which I highly encourage you to do. I am going to scroll back up to the top here, make sure we accomplished all of our objectives. So scrolling all the way to the top, let's just review what we've done. So we started off by constructing a stem and leaf plot. Check. We distinguish between a statistic and a parameter. Remember, statistics are from samples, parameters are from the population. We learned the importance of randomization, helps eliminate bias. We distinguished between the different types of sampling. We understood the impact of bias on study results. We identified sources of bias. We learned the terminology used in experimental designs. We learned the 4 principles of experimental design, and we learned about the difference between an experiment and an observational study. Ideally, experiments are better than observational studies, but they're not always possible. Same as it would be better to do a prospective study than a retrospective study, but money and time doesn't always allow that. Okay, so that brings us to the end of this second lecture video. If you have questions, as always, please send me an email.